It's a great honor for me to open this journey, Gretchen and Barry Mazur. I should say that after breakup of Soviet Union, I spent several years in Boston and was lucky to talk to Barry about some pieces of mathematics I was interested in at that time. And Barry is a universal mathematician. So he blends geometry and arithmetic and algebra in a kind of unique artistic way. And I very much admire how Barry does mathematics, how he thinks about mathematics, but also how he writes mathematics and how he speaks about mathematics. When I was in Cambridge, I even went sometimes to the low-grade courses where I knew the subject, but I just wanted to see how Barry speaks about the subject. But more than that, for me, Barry is a man of Renaissance. So it's not only mathematics, it's many other human intellectual activities. So it's hard to name all of them, philosophy, poetry. And I just was lucky once to be at a Kazhdan Mazur seminar on philosophy. And this was an unforgettable impression for me. So Barry spoke about Kant. And I never thought that it could be so interesting. So I'm from former Soviet Union, so I had some kind of attitude to philosophy. And this dramatically changed my attitude to that. So it was just one Barry's lecture on the subject. Okay, let me go to mathematics. So I actually changed topic a little bit. So what was announced will be hopefully in the end. And my main goal is to give some kind of update on a topic we discussed with Barry about a quarter century ago. So today's look of this is like that. So it's mixed motives and geometry of modular manifolds. And of course, former title was just an example of this relationship. And so let me start from very kind of general remarks. So we're talking about mixed motives. But if you consider pure motives, then Langlands and then Clauzel making this precise. So they taught us that pure, let's say, rank M, pure motives of rank M, let's say over Q. So they are reflected in the world of modular forms by automorphic representations. Of GLM over dels, which are algebraic at infinity. So mixed motives, so this is pure motives. So mixed motives, they're built from pure motives. They're kind of successive extensions of pure motives. And so it's very natural to wonder how the automorphic world reflects this phenomena. So one can, for example, ask a question, can we see something of just all of these mixed motives via modular manifolds, meaning automorphic world. And today I want to give some examples and just want to say again that the simplest of these examples is the one we discussed with Barry. And so if you want to look at mixed motives, so first of all, you want to mix the simplest of them, but you want to get a great supply of them. And so like a source of them is a Motivic fundamental group. It's a great source for a curve. You don't need to go higher, of course. This is a great source of mixed motives. And so what we wanted to do today, we want to look at two examples, two if I have time. But the first, we want to take the fundamental group of multiplicative group minus nth roots of unity with tangential base point at 0. And I'm going to show that this relates in a very strange way to geometry of these modular manifolds. Put M here. And this is subgroup gamma 1 Mn, which is a matrices which is like that mod n. I'm going to talk about this in situation when M is 1, of course, but then 2, 3, and 4. The relation sometimes exists for large M as well, but this is where it's really precise. And what we discussed with Barry in his office was the first situation when it's 2. And then the second kind of update is that the story doesn't end here. So basically, what's going on here is when we consider the field Q, but we also can consider some other fields. For example, we can take Q of I. And in this case, this relationship looks as follows. So we would take elliptic curve. So our elliptic curve is CM multiplication. And then consider, again, Motivic fundamental group of this elliptic curve minus p torsion points, or n torsion points. Let me take p, where p is ideal, prime ideal in the ring which acts by endomorphisms of this elliptic curve. And this similarly, in a very similar fashion, is related to this Bianchi threefolds. So who they are, it's very similar thing. So now it's three-dimensional hyperbolic space divided by a very similar subgroup now related to the prime ideal P. And it turns out that this relationship, a piece of it, I can just, I will explain this later on, but this is nothing just but variation on Mazur's modular simples. Here I refer to various modular simples, which actually there is no paper, as far as I can understand. They appear in the work of Ash and Rudolph with reference to Berry in Inventiones in 79. If this is correct. But at least that's what's written there. Okay, so I'm talking motivically.
You mean the modular symbols for higher Bianchi?
Bianchi, GLN.
Yeah, I see.
Okay, I'll define them. But so
the same question. On the right-hand side, you seem to be limited to m equal to 2. Is that?
The results are limited for m equals to 2. So
you expect the same?
It's a good question. So, I mean, please ask me this question at the end. I mean, I cannot explain the story before I explain what's about. So, okay, so I started to talk about motivically, but as we know, motives, they can be seen in realizations like Elliptic or Hodge. And I choose a language of Elliptic because it's kind of more arithmetic today. And so when we sit at the Elliptic side, so the Galois side, so we see the following, that first of all, we start with Motivic fundamental group, but we have its Elliptic realization, which is given by the pro-L completion of the usual topological fundamental group of punctured C star. And we can linearize the problem. So via Maltsev completion, we can replace the group, which is a huge pro-Elliptic group, by a Lie algebra, which is pro-nilpotent Lie algebra over QL. And it's free with n+1 generators, as it's obvious from the description. Now, what do we see when we look at this object? So, first of all, this Lie algebra, it's Elliptic Lie algebra, it carries canonical Galois invariant weight filtration. Let's call it W. And in this particular case, it happened to coincide with lower central series for this Lie algebra. So it's filtered by commutators. Now let's look how it actually looks like on the picture. So we start with the biggest quotient, which is first dimensional homology of Gm minus mu n. I tend to omit the index, the upper script L, because eventually the story is elliptic after all. And so this is kind of the whole thing, less than 1. Then the next quotient is double commutators, which H2 of H1. So this is less than -2, and so on. Then goes triple commutators and so on so far. And so now what we wanted to do, so I wanted to explain how Galois groups enter to this business. So what we do, we restrict, so forget to say that of course the Galois group, the absolute Galois group, acts by symmetries of these objects. That's the main point. And we wanted to actually understand how the Galois group acts here. This is the main goal. And we want to understand how it acts here and how it sees these modular manifolds. So we restrict to representation phi n L of the Galois group of Q bar over field is obtained by adding all else roots of unity and n. And so now it acts, so it maps to automorphisms of this huge elliptic Lie algebra. And so what we wanted to do, we wanted to consider the image and linearize it. This means that we introduce some graded Lie algebra which depends on n, which is the following thing. So you take image of this Galois group, and you take the Lie algebra of this, and don't stop, so you consider the associated graded quotient for the weight filtration. This makes this object kind of more canonical. Now, what we get and what we're after is a Lie algebra, so it's G dot. So it's just direct sum of G minus 1 plus G minus 2 plus G minus 3 and so on. And we wanted to know what the spaces are and how the commutator works. It's a graded Lie algebra. Okay. Now, let me explain in a kind of in slightly different way. So this is just kind of definition, which is a little bit enigmatic. So what we're actually doing for any integer 0, 1, 2, and so on, we look at a Galois group acting on the following things. So we have this filtration. So we take some number k and consider a quotient of amplitude m. So for each k, which is -1 and so on, and for given n, we consider these quotients of our Lie algebra. And then Galois group acts on this already finite dimension quotients, but there are infinitely many of them. For all k, we just kind of take something of amplitude m and then push it to the end and look what we get. And then we see that we get some maximal Galois subgroup which acts trivially there. So therefore it produced to us some tower of fields. So we have a tower of fields, like we start with Q, then we have the field F1, which is nothing but Q of zeta L infinity n. Then we have the next field F2 and so on. And we can record the Galois group. So this is clear. This one is a new one, so we call it G1. Sorry, it's numbering wrong. It's F1, F0, F1, F2 and so on. So this is G2 and so on. So we get these groups, and they are abelian Elliptic groups. So we can consider the Lie algebras. And the point is that, let me write general definitions, that GM is a Galois group of this Fm over F0. And the Galois group of this extension, which is cyclotomic with a little bit more quotient, acts on this guy. And we wanted to consider the Lie algebra of the
definition again of you consider the Galois group acting on W minus K divided by this.
So what I wanted to say is that so far I'm talking about this abelian quotient, like for example, first of them, okay? And so what I wanted to say that I wanted to consider this Lie algebra, and this is the same thing which we introduced before. Okay?
So what is the definition of Fn?
I write it but didn't say. So you consider these quotients. So for example, you consider the zero quotient, and then you're just talking about a Galois group acting on the homology, Elliptic homology. So you get what you get. So then you consider the first quotient. Now you're talking about X1s. So you have your filtration. This is associated graded, and you consider just extensions, all possible extensions. And so you ask the question, basically what kind of extensions you get. And so you consider, you take the image of the Galois group and you basically ask the question what the image is. And so F is the corresponding field. And so, for example, you can ask the question, what is this G minus 1? And the first thing you see is that you better go to the dual, because the dual has a very nice description. This is, O star of the, let's call scheme SP, which is just the spectrum of the cyclotomic field with 1p added, tensor QL of 1. So that's how the first guy looks like. And so what we learned here is that first of all, we better look to the duals than to the spaces, because they have nice description. And so this is just the group of cyclotomic units. So the group of cyclotomic units tells you what this guy is. Okay, so now you can ask the next question. So how about oh, where is this thing? Yeah. Okay. So you can ask the next question. How about the thing which has depth 2 from this point of view when m equals 2? And so when m equals 2, you're talking about Lie algebra structures, this G minus 1, which you already know, and G minus 2. It's a graded Lie algebra over QL. And so what we want to know the commutator map, which goes from H2 of G minus 1 to G2, G minus 2, because there is no other possible commutators here. And it turns out that, as before, it's much better to dualize the picture and look to G minus 2 dual to commutator map going to H square of G minus 1 dual. So this is the guy which we wanted to see. And we wanted to describe this guy. Okay, I can actually start describing this guy, but I want to make story kind of more elementary, at least for exposition. So what I wanted to do now, I wanted to go to some quotient. You can call it cyclotomic Lie algebra. And so this guy is G minus 1 plus G minus 2 plus and so on. And I want to consider surjective map to something which I'll introduce in a second, C minus 1 C minus 2, and so on. So this actually will be, it's actually not even isomorphism here. So I'm going to get some quotient Lie algebra in a natural way, and then talk the whole lecture about this. So how you define this quotient? All right, you notice that geometrically Gm minus nth roots of unity embeds into Gm. And therefore, if you, you can consider the corresponding fundamental Lie algebra, Lie group of the fundamental group here, which is just QL of 1. And you can map the fundamental group, better to say the corresponding Lie algebra, to this one, surjectively, of course. And then you get the kernel, which is the codimension 1 kernel of this map. Oop, forgot to say kernel. And what I wanted to do, I wanted to consider some depth filtration. Its role will appear later, so far just a definition. So it's by definition just lower central series of this codimension 1 ideal I. And then I have two filtrations, weight, which is completely canonical and works for any variety, and depth, which is very specific. It just uses this specific case. And so we introduce the following quotient. So it's G minus W minus M. So I define this as a quotient with respect to depth filtration and with respect to, I can just say what I already introduced, G minus W of mu n. And this is minus M. Once again, so what I'm doing, I'm introducing one more filtration on the topological object, on the fundamental Lie algebra. Then it filters everything, like derivations, the image of the Galois group. It induces some filtration on the image of the Galois group. And I'm cutting out my Lie algebra by introducing the C minus M of mu n to be just diagonal part. This is just G minus M minus M. So here one can easily see that W is always not less than M. But here we just took the diagonal part. And as you will see, this makes just presentation simpler. OK, so what do we want to do? So we wanted to understand this Lie algebra. And so the same questions about this Lie algebra, how the commutator looks like, and how the actually, I just realized that I told you a lie. I beg your pardon. So, I mean, this isomorphism with cyclotomic units is C minus 1. That guy is biggie. I beg your pardon. This is the units embeds, but that's actually it's okay. Yes, it's okay. 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 So everything else in a bigger weight. It's okay. It's correct. Okay. So there's no lie. So I want to understand this Lie algebra, and what does it mean to understand some Lie algebra? So we wanted to consider the cochain complex of this Lie algebra, because in particular it tells us about the commutator. So we consider the standard cochain complex. So we take, I introduce notation, this Carly C W of mu n is going to be dual CW, and this is supposed to be minus M, and this is supposed to be M. It's supposed to be dual vector space. And now this vector spaces form, of course, a Lie co-algebra. So this means that I will omit n's now. I have a co-bracket, which is going to wedge square of C dot. And then I can continue the story. I can go to wedge cube in a natural way, wedge 4, and so on. So we got this complex, which in particular contains the information we were looking for, the co-commutator. So if we know this complex, we, of course, know more than we wanted to know. We know the Lie algebra and its cohomology. But this complex is graded by this degree m. And so what we can do, we can take the m's part of this complex and consider its cohomology. And so this is a guy which is denoted cohomology of degree m of this C dot. All right. Now I can state the theorem. This is the main theorem at this moment, which tells you who this cohomology are, assuming that my level is prime. Okay. So let me give you somehow a picture of this cohomology computation. So on one hand side, you wanted to put the cohomology of this Lie algebra, cyclotomic Lie algebra of mu p, level p, of degree m. So m is going to be 1, 2, 3, and 4. And so if you want to consider the corresponding cohomology, we are talking about complex. And this complex is very simple at the beginning. This is just C1 of mu p. And here I'm going to put the answers. And we know what it is. It's just O star of this SP. And it's just one vector space. So this is this guy, tensor QL. Then if you go to the level 2, you get C2 going to wedge 2 of C1. And the cohomology here turns out to be H1 of gamma 1 2p with the coefficients in determinant representation. Everything tensor QL. I'm not going to keep writing this. And here we get the same thing, but H0. And Barry, this is exactly what we discussed in the office. Now we want to continue. So we take C3. Then we go to C2 tensor C1. This is just the standard complex in degree 3. And we get here H1 of gamma 1, now 3p, and standard coefficients. And then we get, let me think actually, yes. Then here we get H2, and here we get H3 of the same group. Now we go to the weight 4. Then we have C4. It goes to wedge 2 of C2 plus C3 tensor C1. Then it goes to C2 tensor lambda 2 of C1, and it goes to lambda 4 of C1. And here, of course, we get gamma 1 4p. But the numerology is that we get here H3, H4, H5, and H6. And little caveat, so here we get some quotient, which actually I don't know. I have a conjecture what the subspace is, but I can, yes?
Do you have trivial coefficients?
Yes, thank you, Maxim. They alternates, epsilons is determinant. Thank you very much. So what you see here, that this is what I promised, that you start with the Galois theory of Gm minus mu n, and you write down the complexes, and complexes delivers you, when you look at the different grades, cohomology of these groups. And now you can ask whether it's maybe coincidence, because if you look at this group, all right, so I claim they're the same, but dimensions of this group can be easily calculated, just some number which depends on p. You can find formula in any textbook, and maybe it's a combinatorial accident, and this will be 0. So maybe it's not there. But if you look at the other groups here, if you look at this whole region, then this is precisely the Caspidal range. It's quite amazing that you catch precisely the Caspidal range of these groups here. And for the Caspidal cohomology, we know, of course, that's sporadic. if m is bigger than 2. So you cannot write any formulas for this for dimension. We know that these vector spaces can be non-zero, but we have no formula, no prediction, nothing. So we cannot say basically anything about the spaces as far as I know, except running program and ask computer what the number is. But nevertheless, that's what we get. So now we can say unmistakably that yes, we see this modular manifolds sitting somewhere in the fundamental group. And of course, this was not an accident. Okay, so now the next question was behind this. So I said that we have the isomorphism between cohomology of this guy and this group cohomology. But when one proves this, of course, we get much more. So we get isomorphism of complexes. And so I'm going to tell you that, I mean, we are going to see in a few minutes that actually not only cohomology, but these complexes are realized inside of the symmetric spaces. And in order to do this, I need to remind you a little bit of geometry. So how we approach cohomology of discrete groups. So we consider the corresponding symmetric spaces. And so let me remind you that we have this symmetric space HM, analog of the upper half plane, which is defined as the quotient of GLM R modulo R star plus OM. And for us, it's going to be the collection of all positive definite quadratic forms on a vector space of dimension m over real numbers divided by the positive real numbers. And it's also important that it sits inside of its natural compactification, not Borel-Serre bordification, but just some compactification. And this is just same definition when you consider non-negative quadratic forms. So do the same thing. Now we can introduce the corresponding modular manifolds, officially, so to speak. So Y1MP is going to be the quotient of the symmetric space by gamma 1 MP. And so we're after topology of these guys. Now, how we approach this? So first of all,
so when you consider this compactification using semi-definite form, you also divide by R plus star or R?
Yes.
And what do you do with the zero? You include it? I mean, I don't.
I delete 0.
You should write it maybe.
Oh, maybe I should write it.
Not equal to 0 later.
Okay, yeah. So, but what do you think about this? How we think about this? We take a lattice, which is a lattice. So you want to say what is GLM Z of rank M in the dual vector space. And then we do the following construction. So if you have any element of this lattice, it produces a quadratic form, phi sub f, which is defined as follows. Okay, so we have a functional f sits in Vm star. So we can take this functional and evaluate this on any vector. So we get a linear function, and so we take its square. So it's a quadratic form, but it's a very degenerate. It's rank 1 quadratic form. So it lives in the compactification. Now, if we have a basis in this lattice, so if you take a basis, F1 and so on, Fm of Lm, then we can do the following thing. We can take a convex hull. Let me just do it like that. Convex hull of these degenerate forms. And so this is a very simple thing. It's just a linear combination of those. Just remind you what's a convex hull. Phi I, when I goes from 1 to m. And we assume that lambda i's are non-negative. So that's the definition of the convex hull. OK, so what do we get? So now, if you take this thing and project to the modular manifold. So what we get, I want to have some notation for this. Let's denote this like that. Phi1 star and so on, phi phi m, which belongs to homology. I'll tell you in a second why, of gamma 1 MP, Borel-Mull homology. And this is the definition of, these are Mazur's modular symbols. So look at the paper by Ash and Rudolph, and in 79 and Sionis, you'll find the same definition there. So what Barry noticed, so first of all, you want to see an example first. So the example is when m equals 2, then you have an upper half plane. And so in an upper half plane, you have this famous modular decomposition. And so what you get at this moment, you get these lines. So for example, line going from 0 to infinity. And so when you project them down, let me put it this way. So when you project them down to modular curves, you get some strange objects. So you get triangulated surface, topologically triangulated surface, because there are cusps at infinity. And so what Barry did, so he generalized this picture for GLM. Now for GLM, you have a similar guys. And a very nice thing about them that they are cycles, because like here, the boundary of this guy belongs to the boundary of the space. It's at infinity. Here again, if you take Barry's triangle, then its sides really belongs to infinity, because this is linear combination of m minus 1 rank 1 form. It's of rank at most m minus 1 in a space of dimension m. It's on the boundary. This means that we got a cycle. It's a very, very simple observation. It's a crucial. So we got a cycle. We got a homology class. Then they generate the homology group. And so these are modular cycles. OK, now the next thing to do, we wanted to relate this to the original problem. And so we wanted to use Mazur's modular cycles to relate them to the following thing. So first of all, oh, yeah. There are some lines here. So these modular cycles, Mazur's modular cycles, they produce you a way to catch those guys, precisely those guys. So you consider this line, and so you can call it Mazur's line, because that's exactly where the homology which we constructed live. And it shows also that if you consider anything to the right, you get 0. So this is the top dimensional homology you can possibly have, and they live here. And of course, what we wanted to do, we wanted to relate them to this line directly. And so I would call it Milnor line, because this reminds very much to me this kind of idea of Milnor-Cassirer resolution by Motivic cohomology. But the cohomology of this line closely related to Milnor-Cassirer. But OK, so you wanted to send that line to this one. So let's do this. And this is just a one-word construction after little explanations. So we noticed, and this works for any m. So we noticed, first of all, very elementary observation that the group GLMZ acts on lattice on the basis of our lattice. And if you mod it down by the subgroup we are after, and take linear combinations of the points in this finite set, then actually, even before I take the, just when I take the set, I can describe it, because this is just finite field P to power m minus 0 point. It's a very elementary observation. And so now we have the key point. So we consider a map as I said, this Maser goes to Milnor. So we consider a map from what? So we take this cycles which we get by which are span of Maser's modular cycles. They live in Borel-Moore homology of dimension n minus 1 of this modular manifold. Notice I didn't take the homology group they generate, although they generate homology. I just took cycles, Maser's modular cycles. And I map them directly to wedge M of O star of the p-cyclotomic scheme. And actually, as you will see, I will do a little adjustment. I will add one dimensional subspace later on, which corresponds to Euler's gamma constant. But so far, don't worry about this. So how it works? So first of all, you take any collection of residues mod P. And now you know that it represents some element here. And now when your group GLMZ acts on Maser's modular cycles, so the guys you get are parameterized by this set, but they satisfy some relations like symmetry relations, and when you put plus minus, they do not change. So there's little relations where you satisfy. But it's basically elements of the set. So we take the corresponding cycle here. This is, again, this is Maser's cycle, modular cycle. And we map it to the following unit. 1 minus zeta p to alpha 1, wedge 1 minus zeta p to alpha 2, wedge and so on, wedge 1 minus zeta p to alpha m. Now, if you, I think Ofer is going to ask me a question at this moment. Huh? You play the role of the Ofer. So your question is what you do if alpha is 0. Exactly. So you just say that we use a symbol, I call it Motivic gamma. This is just some extra element which I just add to the game, which do not talk to anybody else, but it makes the answer much simpler. I can avoid doing this, but the answer will be very explicit but a little less nice. So it's just doing this for convenience, but I believe it actually makes sense. So I believe it's really, you really add to your Tate motifs one more. Okay, so we consider this map. This map is surjective, and so after that you can ask questions. What happens with this map? Is there any kernel of this map? And you can guess that we're going to say that we want to construct a resolution, because this Maser's modular cycles, they live on the right, and I wanted to introduce now kind of high analogs of Maser's modular cycles, and they will provide me a map from that complex to this complex. So now I wanted to do kind of higher. What?
So alpha 1, alpha m are in fp to the m minus 0. And what is ch?
Oh, ch is just chains. It's this Borel-Moore chains. So they're cycles. I just use this notation because my C is overloaded. So so you have in this manifold you have chains of dimension m minus 1. This is Maser's model cycles. They're actually cycles, but I just said chains at the moment. Okay. And they're infinite, so they produce your cycles, but I just use the word chain, okay?
But the map is defined only on those chains or on...
Yes, only on those chains. So I take these chains, and for each, I basically take the span of Maser's modular cycles. Just take the linear combinations. For example, if you get 0, it's supposed to go to 0, and so on. So is that okay?
Okay, so this is the transform under GLMZ of the... Okay.
This is, yeah, okay. So now I wanted to do the resolution of this. Okay, my blackboards are the nice ones are limited. So let's go here. No. Beautiful. So, what kind of resolution? So remember this modular picture, so I'm going to erase it. But what I wanted to do, I wanted to take this group which generated by Mazur's guys, and I wanted to write a resolution. I skip Borel Moore here, but they're all kind of in this setup. And so in the end of the day, I'll go up to chains of degree 2m minus 2. And this is on this modular manifold y1 of m. So I wanted to build this, so we don't yet have it.
So is it a group of chains or modulo homology?
Let's wait till the definition. I think it would be better when this is definition. So far, just some abelian group. And so they're not cycles any longer. So there is a differential inherited by the differential on chains. And we wanted to map this exactly where we wanted to map them. We want to map them to wedge M of O star of SP. This guy we wanted to map to the next guy, which is C2 tensor lambda M minus 2 of C M minus 2. No, C2 M minus 2 of C1, and so on. And the most interesting one, we wanted to map to the Cm of my mu p. So why emphasize this? Because we really, after this guy, we really want to know what this guy is. And so what we did so far was, from the point of view of this Galois-Lie algebra, okay, it was okay, but we didn't catch the main guy. This is where our interest is. So how we do this? There's a construction. The construction goes as follows: a generalization of Mazur cycles. But it starts to remind, you'll see what. So by the way, so if you do this construction for m equals 2, you'll recover triangles on that picture. So for m equals 2, you have these guys and these guys. This is a complex. Now, key geometric construction. So let's take any basis f1 and so on fm, and let's complement it by one more vector f0, which makes this sum of them equal to 0. And then I wanted to construct some chain which depends on these vectors. And this is going to be, after projections, this is going to be something, I mean, right now it's going to be something which lives in 2m minus 2 chains of this symmetric space. And later on, we will project it down. So we're just doing some kind of generalization of this modular picture. So the construction goes as follows. So we take a circle, and we put this m plus 1 vectors on the circle. Put here f0, f1, f2, f3, and so on, fm. And then we take a plane trivial tree, which is which labeled by these vectors.
So what dimension is that? That's just the graph?
This is just the graph. It's just the graph. So you take a graph, and you make this plane trivial tree. Let's call it T. Now, first of all, you notice that if you happen to have an edge of this tree, for example, this one, then what you can do, you can cut this edge. And then you have two trees. So you have this tree, and you have the other tree. But each of these trees is labeled by the vector. So what you can do, you can introduce vector. So you assign to E vector f sub E, which is defined as sum of several of these vectors. So in this case, it will be sum from f1, f2, f3, and up to this point. You can say, OK, why don't you take the other tree? Your construction is not canonical. The answer is, well, we can take the other one, but since they sum to 0, we get negative of that. So if you take this tree, so here you get f sub e, so you get negative f sub e. So it's almost canonical. So now we can use this as follows. OK, let me let me come here. So I define the cycle phi of f0 and so on fm to be sum over all plane 3-valent trees T labeled or decorated by your f0 and so on fm. So basically, you take all pictures which I draw like that. It could be different pictures. You consider all of them. And for each of them, you do the following thing. So the most important thing you do, you take the convex hull of the following guys. So remember, I got vector f sub e. But if I have a vector f sub e, it gives me quadratic form f sub e squared, which I denoted by phi sub e. And so I take the convex hull of these many vectors, phi e1 and so on, phi e2m minus 1. Because there are exactly 2m minus 1 of the edges of this tree if you label by this basis. And therefore, it produces you a simplex of dimension 2m minus 2 as we wanted. But that's not the end of the story, because we have to take the sum of those guys. And we don't label the edges of the tree, so we have to pay a little price for this. So we put a sign of E1 and so on of E2m minus 1. And this is a sign which is related to the canonical orientation of the plane. So there is one way to introduce a sign here. I'm not going to talk about this. So that's the main construction. And for example, if you take m equals 2, that you really get these triangles. So then the cycle is just 1, because you have these 3 vectors on the circle. Don't mix this circle with that circle. That circle is combinatorial, and this is the boundary of the hyperbolic plane. But then if you consider 3 Mazur's, or actually classical modular cycles, there is unique 2D cycle here, triangle here. And this triangle is exactly the guy which I assigned to it. If you go, for example, for m equals 3, geometry gets a little bit more complicated. I just give you a cartoon what you get, but not very complicated. So you basically get a pyramid, because there will be, in this case, you can have only 2 different plane trivalent trees. And so what you get 2 tetrahedra. But these 2 tetrahedra are joined in a prism. So this is the cycle which we constructed for m equals 3, and so on and so on. All right, so we constructed a map. We didn't construct a map. We defined this group so far. Now, before I go to the rest, it's very easy to go to the rest of the complex from here. But I wanted to tell you more important things, how we go from here to here. So who goes to whom? Here I don't have, unfortunately, time to explain the construction. I'm just saying that it's kind of key Motivic construction. It turns out that one can define for any, if you have any roots of unity, for example, in mu(n), then you can define, actually, if you take any collection of points on GM, you can still define some elements. So I call it Motivic correlator of this, in this case, units. And I assume for technical reasons that their product is 1 to match the construction. And so where this guy lives, it lives precisely in this C minus m of mu p star. Not star, it's already dualized. So I claim that I can define for you absolutely canonical elements which live in the Motivic Lie algebra. They become so canonical because I took at the beginning associated graded for the weight filtration, but they're absolutely canonical elements. There is no dual Lie algebra, yes. Very important, dual. So all kind of work is in the dual. You never work with Lie algebra, you always work with the dual. That's where you see these objects. Okay, so now you have these objects, but you also remember that there's one more game you can play with motives. You can take the Hodge realization. And so what happens? Because I didn't tell you anything about these elements, and actually forgot to tell you the main thing. that how this construction works. So, okay, let me do it here. So the main construction takes a cycle phi of alpha 0 and so on alpha m. This is a cycle I can define upstairs with generalization of Mazur's modular symbols. So now it's a cycle of dimension 2m minus 2. Not a cycle, it's chain. It's boundary, not 0. And so we map it just to this Motivic correlator of zeta p. You take some root of unity raised to power alpha 0 and so on, zeta p raised to power alpha m. And so you land, as I said, in this Cm of mu p. And so in the end of the day, that's how you get the map. So this map now constructed modulus effects that I did not explain to you who these guys are. But I'm going to tell you not who they are, but how they look in the Hodge realization. And okay, why don't I erase this? So notice the following, that I have this Lie coalgebra Cm, and I was talking all the time about its elliptic realization. Now we do have mixed motives, mixed state motives. We do have Motivic fundamental group, for example, defined in our paper with Delin. And so we can consider now this as a Motivic guy. Now we have a new game to play. We can go to the Hodge realization of this Lie algebra. And then there is a canonical period map, which is not at all obvious, but it's constructed in my paper on Hodge correlators, some absolute canonical map from here to real numbers. So in the end of the day, if you start with this guy, which lives here or here, then you get a number. And so you can ask the question what this number is. Actually, these Motivic correlators, if you understand a little bit this Motivic philosophy, then all you need to know coproduct in this Lie algebra, and I can tell you it explicitly, maybe in a second. And you need to know the Hodge realization of this guy. Then it's uniquely determined over number fields. So all I need to tell you, what is this Hodge correlator. And it's given by construction, which is very similar to this one. That's why I wanted to present it. So what you do, you again take a circle, but now you label the circle not by vectors, but by your roots of unity. You can take any actual points on GM. Just for convenience, I take roots of unity. And then consider the same plane trivial tree. So in this case, like that. It's exactly the same combinatorial setup. But now they are decorated. So they're decorated by those points outside and by some points inside, like y1, y2, y3. So before we took the edge, nh, E, and we assigned to this H something, which was used as a building block. Now we do the same, but this something is going to be a logarithm of absolute value, in this case y1 minus y2. And in general, this is just a green function of these points y1, y2. This answer we get because we normalized appropriately using the tangential base vector. So we just assign this guy. I just call G y1, y2 for short. And then we do the following construction. So we consider these green functions assigned to the edges, g e1 wedge dc of g e2 wedge and so on wedge dc of g e to m minus 1. So notice that this is form of dimension 2m minus 2. And then we integrate this over our CP1 to all internal vertices, this y's. And then we take the sum over all plane trivial entries as before. So this is kind of identical combinatorially to this construction. You also put a sign, of course. So it's kind of identical, but we put green functions instead of putting here these degenerate quadratic forms. So you get a number. And so there is a theorem that this number, this is the canonical period of the Hodge realization. So this means that this determines uniquely who this guy is. And okay, I actually don't have, maybe I have couple of minutes because we start a little later, but I unfortunately don't have time to tell you how you define the intermediate steps. It's very easy and kind of mimic the construction of this cochain complex. I defined you C4, and you know C1, and the rest is kind of wedge products. Here I defined you this CHO, and the other CHO are wedge products of them in some sense. So it's very easy, but I skip this. But rather than doing this, I wanted to tell you a little bit more on what happens next. So now we come to the story about Bianchi Threefolds finally. So, okay, let me do it. Just take a few minutes, 2 minutes, 3 minutes. What to sacrifice? So as I said, the story before was concerning GM minus mu n, and we played basically with roots of unity. And this is kind of high cyclotomy game because we started with cyclotomic units. They describe the simplest piece of the Galois group, and then we went up and got the rest of the cyclotomic Lie algebra. Now we want to go to elliptic curves, and here's what we get. So first of all, the game with Motivic correlators can be played on a universal elliptic curve. So take universal elliptic curve. Then we get here something which I called Euler complex. Just the same game, so get some complex C2 of elliptic curve and n torsion points, going to wedge 2 of C1 of elliptic curve n. So this is the same game with Motivic correlator. So this is Motivic, kind of Motivic guy. And this Motivic guy related to pi 1 of universal elliptic curve minus n torsion points, in a way which can be specified very precisely. So we start here. Now we can go 3 different roads. So you can go to the cusp, which is our cusp SP, and then we get today's story for m equal 2. It turns out that this complex specializes exactly to the complex which describes this first non-trivial quotient of cyclotomic Lie algebra. So it is an explanation, in talking to Barry. So in your office, I was talking about this. This is an explanation where the modular curve come from here. This is really a modular curve, so geometry is there. Secondly, why it's called Euler, why I call it Euler. So I define this guy, but you can go here to this guy produce you 2 Ziegler units. You can take their class in K2, and this is precisely Beilinson-Kato Euler system. So that's why the name. So this lives in K2, and this lives at the generic point. But you can also go to cyclotomic point, or to CM point, like the one I choose today. And then you get a new complex which relates to Gaussian integers. And the answer is that for this complex, for this specific complex, so you can call it something like C2 of some prime ideal. It's the same notation, kind of wedge 2 of C1. So it relates to Bianchi manifolds. So this is the last thing I'm telling you. So what Bianchi manifolds do, they first of all, you start with the n-log of the modular decomposition. So you take a rectangle with vertices at 0, I, 1, and 1 plus I, and do it like that. Now, if you put this on a hyperbolic space, you get a picture like that, and you kind of make it grow to infinity. And then you also add this guy, so you get some kind of thing which is octahedron. And this octahedron, they are analogs of my triangles. And now the game goes as follows. This, when you project down to the modular manifold, this guy goes here, this triangle goes here. The cohomology turns out to be given by H1 of gamma 1 2p and H2 gamma 1 2p. I want to notice here's some portion which I don't completely control, but here it's an isomorphism. I note that that's exactly the range where the cuspal cohomology are, so you again get cuspal cohomology in the end, starting from the Galois theory. And even more interestingly, you see that you get these octahedrons, and you had some cycles here. I start to rush. So this is 1 and 2. It's homology. So there are some homology class here, which is sporadic, Caspel homology classes. They tell you that the elements, the Motivic correlators which you see here, satisfy some relations which we do not expect at all. And we don't know how to describe them except going through this picture. So we know that they exist, but that's it. So that's the end of the story. So, the very last thing that I have a student, Kolya Malkin, who in his thesis explains how the story goes when you go to the whole Galois algebra, don't cut it as we did. And we get here cohomology of these guys with coefficients and symmetric powers of the two-dimensional representations, the same story. Okay, sorry.
Questions? Comments? The remark, actually, I remember in the 90s when I thought about graph cohomology, there was a thing which never developed. It was very, very similar. I think it's almost the same. If you consider not punctured curve, but closed curve, and consider derivation of Rennie-Pot completion of Lie algebra, you get the cohomology of this Lie algebra are the same as cohomology of kind of graph complex which is responsible for automatism of free group. It was kind of Lie version of graph complex. And this is very similar to things with punctures, which is very close relative, and complex have lengths growing linearly in dimension, not quadratically like rails.
Yes,
So I think it's really about graph complexes.
Yes, I think so. I didn't tell you how to define Motivic correlators, and I do use your work. So, for sure. Yeah.
So the cycles, there's the chains that that generalize modular symbols. They're not cycles.
No.
And their boundary. What can you say about their boundaries? What can you say about?
Thank you. You give me a chance to tell you the answer. But it's quick. Okay, maybe so you see better.
And I have a follow-up question, which is there a similar structure for Hecke operators than there would be on the modular symbol?
That's a good question, so I don't know a good answer to this question. So if you go to the cohomology, sure, the Hecke operators X and so on the level of complexes. But look, the answer is the following. So you start with this guy, which basically a circle with collection of vectors, F0, F1, F2, F3, F4, F5, and so on. And what you do, you cut it. So you take one of the vectors you like, for example, this one, and you take the arc here. You cut it. So after you cut it, you see that you have two semicircles. But when you cut it, you inherited, like here, you inherited three vectors. So you put them here, but they're supposed to sum to 0. So you put the fourth vector here. So you get 1, 2, 3, 4 vectors, but you get one more. That's the answer. So you have to take sum of all possible cuts. So the answer is very, very simple. And of course, the theorem is that Motivic correlators co-multiply in the Motivic algebra exactly the same way. That's why it's a map of complexes. And you also see why it's easy to define kind of all cycles in between. You kind of take wedge product, in this case, the convex hull of the construction you already know. For example, your construction, the simplex is just convex hull of these three guys. That's why we have the wedge product, wedge M. That's it. It's very simple. Yeah.
So first of all, a remark. In your picture here, the H6 is still in the Caspidal range in the bottom line, right?
I think H4 and N5 in Caspidal range. Sorry? I think H4 and N5, if my memory is correct.
Is it 5, the middle degree?
The middle degree is 4.5, so it's 9 divided by 2. So it's a segment which is, again, it's 1 for SL2, 2 for SL3, 2 for SL4, and the center is middle, 4.5.
Okay, the next question is 2 years ago we were listening to Katesh. So do you understand the plausible relation with them?
No. First of all, I wish I... this story is the beginning is very old of the story, so it's like quarter century old. And at that time I saw about this numbers like 1, 2, 2, 3, 3, and so on, and notice that they correspond to X1, but I have no idea. X1 Hodge X1, I thought. I have no idea why it appears. It's interpretation of Zuckerman and Wogan. And so what Venkatesh does, he explains, he gives a huge evidence that actually, indeed, this is not a coincidence. So this kind of capital range is related to X1 of Motivic cohomology, and I have no idea why.
So in particular, you don't get the whole range of the...
I get what I get, up to 4. It's a difficult theorem to prove on the level 4. So like before I did this, when I discussed with Vary, I did the case m equals 2, then in a couple of years n equals 3, and then in a number of years n equals 2, it's already like 20 pages. And I don't claim anything about higher m.
Okay. And my last question is, at the beginning, when we were starting from the realization of the Galois group, it was Elliptic, clearly.
Yeah.
And then it seems that after a while we are...
Yeah. After a while, there was a diffusion to the Motivic world through the wall, yes. And we are in the Motivic.
Yes. Does that mean that there is a Q structure when you...
Oh, of course. The whole story is Motivic. I started Elliptic just because for perception it's kind of easier. Because when you start talking about Motivic Galo groups, you lost your audience. So that's why. But the story is 100% Motivic, and it's very important.
So maybe we can thank the speaker again.